Okay, so in this section, we're going to go over matrix inverses and how they can help us solve a system of equations. Right now, for matrix operations, we don't have a division type operation. The closest thing we do have is something called an inverse, and even that will be some kind of multiplication process. Now, a matrix inverse is a very particular type of matrix, right? So a matrix inverse is when you multiply a matrix, and if it has an inverse and its matrix inverse, the result is what is called an identity matrix, right? So an identity matrix, noted sometimes like this, is simply the matrix where along the main diagonal we have ones, right? So usually we'll call this I2, right? I3 would be something like this. Okay. All right. Now, one thing that we have here is we notice the identity is strictly for square matrices. So this idea of a matrix inverse would only apply to square matrices, right? So when I say a matrix inverse, right, what I mean is if I have this matrix A, and not all matrices have inverses, right? But if there exists some matrix B where A times B is I, and then we'll say sub n, right, where A and B, since they're square, A and B are both n by n. If the product of A and B and also the product of B times A, right, because as we've seen, that's not always the same product, but if they're both equivalent to I sub n, then we say B is the inverse of A. All right, so we can write it B is equal to A inverse. Right. Okay. Or vice versa, right? This is again, we can also say A is the inverse of B, right? It's just either or is a perfect explanation of the matter here. Okay, now the idea behind matrix inverses is it allows us possibly another way to solve a system of equations, right? So going back to our system, let's say we had an augmented matrix, right? Where we had, let's say, 3, -4, 1, 0, 2, 3, -1, 4, 5, and then, for example, let's see, our augmented part would be 0, 5, -6. And so I just made up this augmented matrix here. All right, so we want to actually kind of reformulate how we represent a system of equations. Right? So one way that we can do that is where if we have this x, y, z being our variables, right? One way we can do that is we can have the coefficient matrix and we have what's called a column vector or a 3 by 1 matrix here, represented by the variables. And then it's equals to 0, 5, -6. So what we have here is just another way to write the system as a matrix equation, right? Now, if you multiply these two matrices, which is a valid operation, right? This is 3 by 3. This is a 3 by 1, and then we have here a 3 by 1. All right, so what you see here, right, those middle numbers are the same. So that means, and that means that I'm able to multiply, and the result would be a 3 by 1 matrix, which is what I should get, right, because it's equal to a 3 by 1. All right, now in multiplying these matrices out, what you'll get is you'll get the system of equations, right? If you just look at kind of, I won't do the whole multiplication here, but if we look at, right, the way we do multiplication, right, we multiply the row times the columns, you get 3x, right? That first row would be 3x minus 4y plus z, right? And we'll see set equal on the other side to 0. Okay, so if we do that with the second row, we'll get the second equation, etc. Right? So this idea of writing it as a matrix equation, right, where this 3 by 3 equation is the coefficient matrix, this column matrix, sometimes known as a column vector, right, your book uses well, I'll just use the notation in your book. Right? And then here the constant column matrix to be equal to B. All right. So the idea here is how we're going to use matrices, inverse matrices, I should say, is, well, I can treat it like I would in an equation, an algebraic equation, right? Where the analogy here is if I had something like, let's say, 3x minus 9, or 3x equals to 9, the way I would solve for that is I would divide by 3, and we get x is equal to 9. All right. Now, the idea here is, well, what I'll do instead is I'll multiply, if it exists, by A inverse. All right, now here you have to be careful. The multiplication, the order matters. So since I'm multiplying on the left, I'll multiply by A inverse. All right, so what happens here, since this is the inverse, the result would be I3. And this would be some product A inverse B, right, which I would calculate, right? Okay, and here notice that x is 3 by 1, the identity is 3 by 3, so this is a valid operation. Now, one of the properties of the identity matrix is that it's essentially like multiplying by 1, right, when we think of numbers, right? So here, when I multiply this, the result would be simply the column matrix X equals to A inverse B. Okay, so it has a way to solve for the values of X, right? Remember, X represents the column of the variables X, Y, Z, right? And when I do that multiplication, A inverse B, right, then the result would be the solution to my system of equations. So that's going to be the goal in this section, right? To solve a system in this manner, okay? And I guess one thing here, just to kind of specify, I didn't go over in the first part, whenever you have an identity, right, as long as the operation is valid, right? So let's say you have matrix C, and really any matrix times the identity, hence the name of the identity, you get back the same matrix, all right? As long as the operation is valid.